talk about logistic models, categorical data, odds. I'll start right here. Just as a recap, it's going to be a weird thing here. Okay, so I'll laser this, and maybe that'll show up on the video. So with our logistic models, remember what we're doing is we're regressing a dichotomous outcome variable, well, a categorical outcome variable. Here we're working with just a binary logistic model where we've got a dichotomous outcome that we're looking to regress onto a series of categorical and continuous predictors. Okay, but what we're probably looking at is wanting to regress a probability, right? What we want to know is what's the probability of this outcome or what have you, right? But remember, problem is probability functions aren't linear functions, right? They have this kind of S-curve business going on, and it's also bounded by 0 and 1, right? You can't have a probability over 1, you can't have a probability less than 0, and so as you get closer and closer to those boundary values, you see this asymptotic curve there, right? And so the problem is that we can't, with our general linear models, regress onto a linear model onto a nonlinear outcome because it's not going to be a good fit, right? And so what we end up doing is we end up sort of taking this probability function, and we can get linearity in these parameters, right? But what we end up being is, if we're want to predict a probability, what we end up is base e to our linear function over the top of 1 plus base e to the linear function. That's a nasty, nasty mess, right? So we still have our linear model in there, it's just in a weird proportion. And so what we do, though, is because our probability is nonlinear in its parameters, what we can do, though, is we can transform that nonlinear function so that we can create, sort of estimate a linear model that then we're predicting the linear transform of this probability function outcome. And a lot of different link functions that you see. You'll see different types of probits and things like that. Depending on what type of data you're looking at, you may use a different link function. But the most common function that we see is the regression of a logit or a log odds. And so basically, if this is the probability function that we're trying to predict, we can't do that easily within our basic general linear model. But what we can do is we can transform this and solve for just the linear equation. And what we get here, at least in the natural log, or in the most standard form, is a linear model that's predicting the natural log of an odds ratio, okay? And so what we do with our logistic models is we're predicting not our probability outcome. That's what we wanted, but we can't get there. But what we can do is we can take that outcome, that 0-1 outcome, and go through, translate it into the natural log of an odds ratio, so the odds of an event versus the odds of a non-event. And what ends up happening is then we can use this logit or log odds and predict that with our general linear model, okay? So here you can see linear regression equation on this end, predicting the natural log or the probability of being in one group versus the probability of it being in a different group, okay? So we've got a log odds going on here. Our logit or our log odds is linear in its parameters, okay? So it can be 0 to infinity, okay? Or no, negative infinity to infinity, right? So natural log of your odds is linear in its parameters. It's continuous. What we're doing is determining the odds of being in a particular category versus another, given a set of predictors. But the thing is, remember that this is going to be different than our standard regression model, where our regression equation predicts our outcome, right? In our logistic model, our regression equation isn't predicting the outcome. Our regression equation is predicting the natural log of the odds of being in category A versus category B, which adds a little bit of complexity to this, but it's not anything that we can handle as long as we know what we've got going on with this stuff, okay? Questions on sort of how this model is set up, what we're doing, and why we have to set it up this way? Feeling good about this? Okay, cool. So again, we had talked about maximum likelihood estimations, or some of the stuff there, the demonstration about maximum likelihood, how that's working, right? So jumping into our example, okay? Let's say, and if we look at have a binary logistic model, this is looking at an outcome that just has a dichotomous, sort of either it happened or it didn't, right? Now we can get into more elaborate models where we have multiple categories, right? So we have, so you can be in category 1, category 2, or category 3 as your outcome. Refer to these as multinomial logistic models. But at the end of the day, what you're still doing is you're still sort of breaking that down into a binary logistic model, because what you end up doing with that is you have a series of models that are predicting sort of some outcome versus a reference group, right? So if I have 3 outcomes in the multinomial, right, I can't predict the probability of sort of all of these 3 together. What I end up with 2 models that either predicts the outcome of B versus A or C versus A, and so again, we have to have some sort of reference group with that. Now, I've given you a handout that goes through an example of a multinomial logistic regression. You can take a look at that if this is something that ends up coming up in the course of your research. You can go through read to batching of the Dell. Would strongly recommend that you do that anyway. But we won't worry about multinomial models here just because we don't have enough time. But for our binary logistic regression, we're looking at an outcome that takes on 2 values, 0, 1. And the purpose of the model, predict the odds of falling into some criterion category relative to a reference category based on our best linear combination of independent variables, okay? And so, again, this is one of the things that becomes crucial. I can't emphasize this enough. As you're going through, you're talking about and going through and interpreting your coefficients in these models, absolutely need to know what category or what level of your categorical outcome is your reference group versus your criterion, okay? Anytime you sit down with this, because SPSS does some things that are not intuitive, always want to make sure, whether it's for your outcome variable or for your predictors, know what the reference group is, what your criterion group is, so that you're interpreting these appropriately. Because if you get that screwed up, you're going to get some funky answers that hopefully you catch and go back through and take a look at that. And when we go through the output, we'll look at sort of how you can go through and check and make sure you know which group is which, because it's going to be important for moving forward with some of this stuff. So, example, I can't remember if this might be Tabachik and Padel, I can't remember. But let's say we have a small model where we want to assess the probability of falling on a ski trail based on difficulty and what season we're talking about, okay? The idea being that we've got a level of difficulty assessed on what we'll call a continuous variable. It's actually not, it's just 3 levels, so this is ordered categorical. This is another thing to be mindful of what your variables are. I mean, this is, for this example, fine, we'll treat this as continuous, but if I were actually putting together a publication, I would be very hesitant to call 1, 2, or 3 and treat that as a continuous variable. There are alterations and sort of variations on this model that you can go through and account for ordered categorical IVs. But then we also have season, right? Season, this is a true categorical outcome. There's no, I mean, time-wise, there's a progression, there's an order to it, right? But there's no sort of meaningful sort of quantitative difference between these two. So in this example, we've got 1 is autumn, 2 is winter, 3 is spring. And in this case, spring, that you'll see the asterisk there, this is our reference group, okay? And so we'll end up modeling this as our, kind of like an indicator regression, where our impact of season will be, our specific effects will be comparing autumn versus spring, winter versus spring, and spring being our criterion group. So the model that we estimate, and here's our data, right? Skiers 1 to 15, whether or not they fell, difficulty of the trail, and what season it was, right? We have our estimated model. What we're doing, and when we run this logistic model, this is our regression equation. This is our regression equation we know and love and have spent so much time with, but our outcome here is not the probability of falling or not falling, right? Our outcome here is the natural log of the odds of falling versus not falling, okay? But what we can do, given this equation, and given what we know how to get into that, how this relates to probabilities, we can, just like for a regression equation, if I want to have a predicted score for Trent, right, and I want to see what Trent's, my model predicts Trent's score is for some continuous outcome, same thing we can do this here. If Trent is skier number 1, I can take this model, this regression equation, and sort of back translate it into and actually get a probability for Trent, right? Basically what we do, given that we know sort of this relationship here, right? What we end up doing is we can take the coefficients from this model, right, and plug them in and take e to the sort of whatever my linear function is over the top of 1 minus e to the linear function, plugging in the season and difficulty for Trent to determine the probability that Trent falls on this ski slope. Okay. So what's up?
Probability of me falling is very high.
Well, so I don't know. We'll see. Depending on the trail difficulty, things like that, we might get different answers here, right? Okay. So, but recognize that this is the model that we're estimating, but we can still take those coefficients, translate them back in to actually get a specific probability for any individual in our sample, just like we would do with the normal regression equation, right? What it ends up being is we just take base e to the regression equation with our variables punched in here and take that over 1 plus base e to sort of whatever our model is there. Okay, and so you'll see we have a coefficient, we have an intercept, we have a coefficient for difficulty because that was our continuous variable, and then we have 2 dummy codes for season. Candace, what do these dummy codes represent within the context of this model?
It's going to be fall. Spring is the reference group, so the dummy codes are going to represent autumn and winter.
Versus
Spring.
Right. So we'll have, this is a coefficient that tells us the increase or decrease in the odds of the natural log of all the odds falling versus not falling for autumn relative to spring, and this one will be winter relative to spring. Okay. So model fit for logistic models, right? So thinking about, we want to have some test of whether or not our model is actually doing anything, right? Similar to analog being our R squared for our continuous regression models. Model fit with our logistic models determined by a log likelihood, where our log likelihood is the sum of our actual outcome times the natural log of our predicted outcome plus 1 minus our outcome times the natural log of 1 minus our predicted outcome, okay? This is just how this is calculated. This is what this looks like in practice for our skier data, right? Here's our list for each of our individuals, whether or not they fell or didn't fall, right? What we do, what SPSS is doing in the guts in the background, is it's taking that and taking that against our predicted value of whether or not a person falls or not falls, right? And this is 1 minus that estimated value. Then we have our actual outcome times the natural log of our predicted value. Here we have 1 minus our outcome times the natural log of our predicted value, and then we get our log likelihood value here. Okay. Well, what you'll notice is depending on sort of whether or not someone fell or didn't fall, if they didn't fall, y times the natural log of our outcome is going to be a number, but here this is going to reduce to 0 because 1 minus 1 is our actual outcome, is 0, and we multiply 0 by anything, and then that goes away, right? Mm-hmm. For people who didn't fall, we don't get a value for y times the natural log of our expected outcome because our expected outcome is 0. We put 0 there, right? And so we get across these two, depending on whether or not a person fell or didn't fall, we get a value here, and we'll see here for someone who did fall. And for this person, it looks like we did a pretty good job of predicting whether or not they would fall, right? Mm-hmm. So 1 minus our expected value is something quite small, and so when we take 1 times our natural log of our small number here, we get a log likelihood value that's quite small, versus the second case where we're predicting this person fell. If we use 50% as our tipping point, right, we would classify this as a fall, and we did it correctly, right? But the problem is that when we take 1 minus this, we get a larger number. When we take 1 times the natural log of this predicted outcome here, it's a much larger log likelihood than this, right? And so what we end up seeing is that our lower log likelihoods indicate better model fits, right? Because if our model is doing a good job, this estimated value should be very close to 1 or very close to 0, right? If it's right around 50%, then we've got a 50-50 thing, then we're starting to get worse off, right? And then we get outcomes like this where our model predicts that a person didn't fall, but they did fall, right? And we're getting larger log likelihoods here. So what we do is we set up this table, add up the log, sum of the log likelihoods, and we get a model log likelihood for the whole thing, which is the sum of the individual log likelihoods for our individual cases. Our model log likelihood can be multiplied by -2 to place it on the chi-square distribution. Why -2? Or why negative? Maybe not 2. I don't know the answer why 2, but why a negative? Why are we multiplying it by a negative number? To make it positive, right? We have negative chi-square values, right? Chi-square distribution is all positive. But if we multiply our our log likelihood by -2, we get a -2 log likelihood. Lower values indicating better fits. And what we can do with this is, if we have nested models, what we can do is we can start subtracting the difference between -2 log likelihood against a base model, and we can start looking at whether or not we have a better model given the inclusion of some variables versus another, versus without. A significant chi-square indicates reliable improvement in the overall model. Yeah.
I don't really understand what a nested model is.
Nested model, let's say I've got, for example, let's say, like, going back to moderation, right? So I've got a model with 3 direct effects, right, or 3 first order effects, and then 2 interactions, right? My model with the 2 interaction effects, or the model with just my 3 first order effects, is nested within my model with all 5, right?
Oh.
And so what we can start doing is we can say, and we'll see this is how we calculate this, is you'll have what SPSS will do is it'll estimate a baseline model and says, what's the fit if we just don't have any predictors in here?
Mm-hmm.
And then what you'll do is it'll compare that against your full model with all the predictors, and the baseline, the independent, or the model that has no predictors in it, is a nested model in with the model with your full predictors. And what you can do is you can look at the chi-square, or the -2 log likelihood of the model with just no predictors in it, and compare that against the -2 log likelihood of the model with all your predictors in it. And what you're hoping to see is a reliable decrease, right? You're looking at hoping to find that difference in those 2 log likelihoods is distributed on a chi-square, with the degrees of freedom being sort of the number of extra parameters in the base model versus the full model. And what we can then do is start to, so if we say, if I had a continuous or a dichotomous outcome, I might test my full model with my 2 interaction variables in there, and then I would estimate a base model with just the 3 direct effects, the 3 first order effects, and then what I would do is I would take the -2 log likelihood from the model with all 5 predictors and compare that with the -2 log likelihood of the model with just the 3 predictors, and if the difference between those 2 log likelihoods exceeds a critical value for chi-square with 2 degrees of freedom, then we would say, yes, it looks like the inclusion of these interaction terms has produced a reliable increase in the overall quality of this model, right? So this is a lot what we'll do. So this is the reason we're going through, not that I'm going to have you go through and calculate this out, but in understanding what the log likelihood is, it's just a broad index of model fit. Lower values are better, and we're going to use this flexibly to go through and test individual predictors and different types of models and things along those lines. Okay, does that help? Any other questions about this? All right. So here's another thing that says, looking at evaluation of correct classification of cases. So here is our classification table for our skiing example. Okay, and if we look with this 2 by 2, here's what we observed, whether or not people fell or didn't fall. Here's whether we predicted people wouldn't fall or they would fall. And it looks like we did okay. Overall, we're about 80% correct, right? But we've got some false positives here. We predicted people would fall and they didn't. We've got some false negatives, false negatives, predicted people wouldn't fall and they did, right? But in general, doing okay here, right? And so what we can start to do with this is, and experimental folks, you may not get into this a whole lot, but it's just a generally useful term in terms of these outcomes, looking at sensitivity, specificity of being able to predict some outcome variable, right? So we talk about sensitivity as the ability of a model to correctly identify a criterion, right? So what we've got is our true positive, right? So the people who we predicted would fall, who actually did fall, divided by the true positive and the false negative. So in this case, we would have 8 divided by 8 plus 1, right? Here's our false negative. We predicted they wouldn't fall, they did, and that will give us our sensitivity. This is going to be the ability of our model to correctly identify a criterion. We had, in this case, we had 9 falls, we got 8 of them. We predicted 8 of the 9 falls with our model, right? This is the inverse of this is specificity. This is our ability of our model to correctly identify non-criterion, right? How good are we at predicting, if we say someone doesn't have something, how good are we at predicting this, right? This becomes important in thinking about drug trials and things like that, right? You know, sort of wanting to have you know, a sensitive measure and a specific measure so that I don't say that Trent has cancer when he doesn't have cancer, right? Because that's going to scare the hell out of Trent. But if he does have cancer, I want my model to predict that he has cancer, right? So we can go through and provide treatment here, right? So specificity is going to be our true negatives. This is 4 divided by a true negative plus our false positive, right? So that's going to be 4 over 6 here. Our positive predicted value is going to be a little bit different. This is going to be percentage of cases identified as criterion that actually are criterion. This is going to be our true positives, again 8 divided by our true positives and our false positives, right? So this is going to be 8 over 8 plus 2 is 10, right? So again, this is going to tell us how confident are we that a criterion is a criterion. So if I say someone's true, if I say someone is a case, how confident am I that they are a case, right? This is different than our sensitivity. Sensitivity is like how many of the cases did we capture in our model. This is saying if we do capture a case, what's our confidence that this is a case, right? Because if I wanted a maximally sensitive measure, I just say everybody has cancer, right?
Right.
And then my sensitivity is 100%. Then we make sure that everybody gets treatment, right? But we're going to be providing treatment to a lot of people who don't have cancer. We're going to be scaring the hell out of a lot of people, right? And so our positive predictive value is telling us if we say that someone's a criterion case, how confident are we, right? And the same thing with negative predictive value. Identifying percentage of the cases identified as non-criterion, right? Correctly identified as non-criterion over all those that actually are non-criterion. We got our true negative over our true negative and our false positives here. No, our false positive is, yes, here. So 4 over 4 plus 2 is going to be 6, right? And this is going to say, if we say someone isn't a case, how certain are we that they're not a case, right? So, and again, a lot of clinical implications for this, but I think some probably interesting sort of translational stuff into sort of experimental types of things too, right? Steph, for you guys, we're going to use one of someone Marine as the example, right? If I predict someone's not going to get the death penalty, how confident am I that they're not actually going to get the death penalty, right? Or if we think someone's going to engage in some sort of risky behavior or something like that, and or this is my model that predicts whether or not someone's actually going to engage in a goal-directed behavior. How confident are we that they'll actually do this if there's some sort of outcome here, right? So here we've got sensitivity. If we go through and if you wanted to calculate this, you'd end up with sensitivity as 0.89, specificity less good, right? So our model here is better. Looks like it's better at capturing people who did fall versus those who didn't fall. And that's probably a function of the fact that more people fell than didn't fall. This is something to be aware of. If you are trying to predict some outcome that has a very, very low base rate, it's going to be tough, right? It's easier to predict something that's happening more frequently than something that's happening less frequently. That's probably part of what's going on here. But our positive predictive value, negative predictive value, both 0.8 in this case, right? So we're equally, although we're successfully capturing more falls than we are successfully predicting and capturing non-falls, we're more confident if I say that, or we're equally confident in saying if I'm predicting someone that's going to fall, I'm probably pretty good there. If I'm predicting someone's not going to fall, I'm probably pretty good there. Okay. So again, sort of twisting this around a little bit. Judy, do you have a question on this?
Yeah, I think so. For the negative predictive value, the true negative is 4.
Yep.
Over true negative 4 plus false negative 2.
No, I'm sorry. False negative. You're right. Is 1, right? So this is 5. 4 over 5. Yep. So negative predictive value is our true negatives, which is 4, and our true negative plus our false negative. So we've predicted that someone won't fall, but they did fall, so that's our false negative. I'm sorry, I got screwed around. I was pointing to false positives. Nice catch. Okay. Any other questions on this? All right, cool. So, test of our individual predictors in our logistic model. Okay. Unlike our multiple regression models, we've got different tests depending on how you want to test your individual variables. We've got different tests for those individual predictors. The one that SPSS provides, and is probably the most common, even though it's the worst, is a Wald statistic. Wald statistic is calculated as your coefficient squared over your standard error squared, with your test statistic distributed as chi-square with 1 degree of freedom. Okay? You have a question?
Looks like it, but it doesn't.
Okay. So what we're doing here is we're taking our regression coefficient, we're squaring that, divided by the standard error of the square of our standard error, and using that and testing that against a chi-square distribution. Now, but what we find from a statistical standpoint, calculation of your Wald standard error, inefficient, and the distribution is imprecise, right? So this standard error for your Wald, as we're calculating it here, has larger variability than we would want in the sampling distribution, right? We want small sampling distributions because that translates into small standard errors, and the distribution is kind of an approximation of chi-square with 1 degree of freedom, but it's not perfect, right? And so we have some problems there. When we run through simulation research, well known that Wald associated with elevated type 2 error, right? Stephanie, if we have elevated type 2 error, what's my problem, what's my concern? What happens when I have elevated type 2 error?
You're saying that there isn't something present and there is.
Mm-hmm. So I'm saying that this is not a reliable predictor with my Wald statistic, when it probably is, right? And so our resulting statistic, unreliable, difficult to interpret when our p-values are marginal, right? So in general, if you get a Wald statistic and p-values, 0.002 or something like that, you're probably fine, right? But if you get a Wald statistic and your test of your coefficient is, say, 0.056 or something like that, you better off switching over to a different estimator or a different test of our individual predictors. Kind of our criterion, our gold standard is our log likelihood difference. Okay, log likelihood difference, going back into what we had just talked about, calculated as the difference in the -2 log likelihood for a model with and without the predictor. Okay, so what you're going to do here is you're going to go through and you're going to run a model with the predictor that you're interested in, and then you're going to run a model with all the same predictors that you had before, but just omit that one predictor that you're looking at, and then you're going to take a look at the model log likelihood for the full model minus the model that doesn't have that, and what are we looking to find probably in the difference of those 2 log likelihoods, Judah?
Smaller is better, I don't know, chi-square, you want it to be significant.
Right. So are we hoping to find a large difference in those model log likelihoods, or a small difference?
A large difference.
Why is that?
Because then you'd be saying that whenever you added whatever you were interested in, like a lot changed.
Exactly, right? So what we're hoping, if we want this predictor to turn out, is we're hoping that we end up with a substantial decrease in the model log likelihood when we have this in versus when we take it out. Conversely, if we take it out, we see a significant increase in the -2 log likelihood. And so what we would do then is we take the -2 log likelihood for our full model, compare that against the -2 log likelihood for some restricted model or some smaller model that doesn't have our individual predictor in there. And then what we would do is test that difference score against a chi-square distribution with 1 degree of freedom to determine whether or not this is a significant, contributing significantly to the prediction of our outcome. Again, hoping that we would see that difference between those two log likelihood values would exceed whatever our critical value would be at alpha 0.05 or whatever it is that we're doing, okay? And this difference in our -2 log likelihoods is our preferred estimate for evaluating the unique contribution of this predictor, okay? Last way that you can go through, take a look, something called the Lagrange multiplier. Just takes a little bit a different approach. So it calculates sort of the overall estimate of model change given inclusion, exclusion. It just takes a little bit of a different estimator. Lagrange multiplier somewhere intermediate to your Wald and your log likelihood difference. So I mean, if you're going to do it, I don't really know. SPSS I'll show you where these tests are in SPSS, and you'll see that it kind of changes. But really here, this -2 log, the difference in your log likelihoods is kind of your gold standard for determining the statistical reliability. Now you won't see, oftentimes people will publish things and they'll just use their Wald statistics because things are pretty cut and dry, pretty clear cut, right? There's not a huge difference, but if you're starting to get marginal effects, it's worth taking a look at that -2 log likelihood. Okay. Questions on this? All right, so our interpretation of our coefficients. For our binary logistic models, we only have 2 outcomes, right? And so we can say the odds of falling are this, right? Because kind of implied in there is the odds of falling versus my alternative is the odds of not falling, right? So we can get away with our binary logistic models talking about the odds of this versus the odds of this, knowing that what we're really talking about is an odds ratio. Now, if you get into the multinomial models, right? Multinomial logistic regression, now all of a sudden you're comparing the odds of this versus the odds of some reference group, right? And then we need to start being more specific when we're talking about what odds we're talking about, right? We're saying the odds of being in category 3 versus the odds of being in category 1, right? But we can sort of streamline our language a little bit with our binary logistic models as long as you know what you're talking about, right? Talking about the odds of it being in one group versus another. But remember that our equation that we're estimating isn't predicting probability, but it's predicting log odds, right? And so our coefficients represent sort of change in the natural log of the odds ratio, which can be kind of confusing to talk about, right? So what we can do to interpret these coefficients is we can go through and exponentiate those coefficients to start turning these log odds back into an odds ratio that we can talk about a little bit more meaningfully, right? So we've got here interpretation of coefficient through facilitated through interpreted exponentiation. So here in our skiing example, our coefficient for difficulty, right? Oops, too far. It was, our coefficient for difficulty was 1.01, right? That was the coefficient that we see in our model. And so what we could do then, because this is a coefficient representing change in log odds per unit increase in our predictor, right? but I don't know what log odds are of whatever. That doesn't make a whole lot of sense to me. So what we can do, and SPSS will do this for you, is we can take this log odds to base e to the power of whatever our coefficient is, and we can get an odds ratio, okay? Our odds ratio is indicating that holding everything, all our other predictors constant at 0, just like and that doesn't change at all, right? The odds of falling are multiplied by 2.5 for 2.75 for every increase in slope difficulty, right? So suggesting that if my slopes are easy, medium, and hard, that my odds of falling increase by 2.75 for if I jump from easy to medium, right? Or my odds would increase from, if I jump from medium to hard, my odds of falling would increase by 2.75, okay? But notice that this is multiplied, okay? What ends up happening, these are a power function, and so if every time I increase, so if I went from 1 to 3, so I had a 2-point change, what would the increase in my odds of falling versus not falling be for a 2-point change here?
Times 2?
No.
Square.
What's that?
2.75
Y squared.
Oh.
Because it's like you're multiplying by that for each unit.
Exactly. And so what if our scale went up to 4 and I would have jumped from 1 to 4?
Then
Cubed.
cubed.
Right? And if it was 4, if I said 5, if there was a 5-point scale, right? So it would be my odds ratio taken to the 5th power, right? And so this is going to be an important thing to keep in mind, because sometimes what we'll get in our models with continuous predictors, particularly continuous predictors with a wide range, right? I'm looking at 0 to 100 scale. My individual odds coefficient, or my individual coefficient, my odds ratio for that predictor may be quite small, right? Because you're going from a score of 5 to 6 on a 0 to 100 scale is going to be very, very small, right? But for every increase that I have, what's going to happen is I'm taking the odds of whatever my odds ratio is and increasing it by that power to say this would be the odds. And so in this case, we may be, if you've got a very, very fine-grained scale, maybe what we would be talking about then is taking a look at what are the odds, given a standard deviation increase in this continuous predictor, what would be the change in odds for falling versus not falling, something along those lines. Do you have a question, Candace?
No.
Okay.
Just processing.
So for an example here, and so if you got categorical predictors, dichotomous predictors, this ends up being pretty easy, right? So you sort of, the odds are of this group versus that group are increased by this much, right? But when things start to get into continuous predictors, you need to pay a little more attention here. So for odds ratios greater than 1, what does an odds ratio equal to 1 mean, Trent?
It's equally likely.
This is equally likely. Really, in logistic regression line, it means it's even money. It makes no difference, right? Sort of whether or not this increases by 1 or not, it's sort of even on this, right? But as our odds ratios become greater than 1, we would say we see an increase in the likelihood of our outcome. So for an odds ratio of 1.5, we'd say the likelihood of an event is 1.5 times that of a non-event, given a unit increase in our predictor, right? So if we had an odds ratio of 1.5 for, in our skiing example, sort of for autumn versus spring, which is our criterion, right? We would say that we have the odds of falling versus not falling are 1.5 times more likely for skiing in the autumn versus skiing in the spring, right? So we're talking about an increase. Alternatively, remember, we can go through and we can take that odds ratio subtracted by 1, interpret it as a percentage increase, right? So we take 1.5, subtract 1, and we've got a 50% increase, right? So the odds of me falling, all things else held equal, increase by 50% if I'm skiing in the fall versus skiing in the spring. Okay. For a continuous, if my odds ratio for my continuous predictor is 1.5, and I say a 5-point increase is some sort of meaningful unit, what I would do is take 1.5, take that to the 5th power, and then I've got close to a 660% increase in the odds of falling, given a 5-unit increase in sort of whatever my predictor is here. Okay. Same thing, odds ratio is less than 1. This indicates a reduction in the odds or decreased likelihood. So for example, we've got an odds ratio of 0.8. We'd say the likelihood, and so you want to be careful as you're interpreting this, right? So you would say the likelihood is 0.8 times that of a non-event, giving you an increase in your predictor. What you don't want to say is the likelihood is 0.8, represent a 0.8 times a decrease, because it's already an odds ratio less than 1, right? So if you're just talking about it, you're just saying the odds of falling versus not falling are 0.8 times, or the likelihood of falling is 0.8 times that of not falling, given a sort of switch from autumn to spring. Right? You don't have to say a decrease because it's an odds ratio less than 1. It already says that. Now, if you want to talk about things in decreasing terms, again, what we can do is we can take 1 minus this 0.8, and we can say alternatively our odds of falling are decreased by 20% by skiing in the autumn versus the spring. Okay, but same thing here. If this was if this odds ratio corresponded to some continuous predictor, right, and we wanted to see what a 5-unit change, change would correspond to, take 0.8 to the 5th power, right, and then we're going to say, and then whatever that odds ratio is, subtract that from 1, or take that away from 1, and so we'd end up saying that we've got a 5-unit increase results in the 67.2% decrease in the odds. Okay? So this is where people get tripped up. If you're talking about this odds ratio and just interpret it as a likelihood, you don't have to say increase, decrease. You just say the odds of an event are 0.8 times that of a non-event, given a unit increase in here. Because you've already, so the fact that you're reporting an odds ratio that's a decimal already indicates that it's a decrease to anybody who's sort of knows what they're looking at, right? But if you wanted to say and really emphasize that, no, this is a decrease in the likelihood of this happening, what we can do is then talk about this as a percentage decrease, right? So if we're talking about odds ratios in terms of likelihood, we're not talking about an increase or decrease in likelihood of odds. We just say what the odds are. But if we want to talk about it in terms of increasing, decreasing, we can take that odds ratio, subtract 1, and then interpret it as percentage. Yeah.
So going up to where we're talking about the odds of falling.
Yeah.
So when it says the odds ratio indicates that holding other predictors constant at 0.
Yeah.
What would, in this example, what would that mean with autumn, winter, and spring? Since spring is my reference, is holding things constant talking about just for spring?
Beautiful. Absolutely fantastic. Yeah, absolutely right. No. This is exactly what you should be doing. Like, think about, like, what does it mean when everything else is held constant at 0, right? Now, remember, these are additive models. So really, when we're talking about everything held constant at 0, we're just saying that once we account for these other variables, this is a unique prediction of this outcome, or this predictor for our outcome, right? Because we wouldn't expect, even if we were to talk about for difficulty, sort of, I'm assuming that difficulty, the impact of difficulty is independent of what season it is, right? So I would expect the odds of falling to increase at the same rate regardless of whether or not it's spring, autumn, or winter, right? What would we need to do if we thought that the odds of falling may change based on the impact of slope difficulty on the odds of falling? If we thought that would change depending on when we're talking about spring, autumn, or fall, what would we need to do? Judah. If we think that the relation between one predictor and our outcome is going to change based on another predictor, what do we need to do to model that?
Put it in the model.
What do we need to do special to it, though? Anybody have an idea?
It needs to be a quantitative model.
Exactly, right? And so what does that mean?
So you need to multiply it by whatever you're expecting to change.
Right, and so what do we call that? An interaction, right? There we go, absolutely right. If we think, so we're saying, and you guys are fantastic, so absolutely right. We're talking about specifically, if we're getting down to the nitty gritty, what this is doing is it's estimating the impact of trail difficulty on the odds ratio of falling for people who are skiing in spring, because that's our reference group. That's what it means when everything else is held constant at 0, right? But technically, within these models, we're assuming a constant relation across all other variables, right? Because it's an additive model. If we think that, and this isn't, if people, anybody ski? No, there are no skiers here. But it wouldn't be unreasonable to think that, depending on the season, that people may be more likely to fall in crappy spring snow or
No
something
snow.
like that relative to another, right? And so, but if we thought that was something that would go on, we would need to create an interaction term, right? So then we would need to have an interaction of season and trail difficulty. We'd actually end up with 2 interaction terms in there, right? One for our first indicator, one for our second indicator to model that. But you're absolutely right. This is saying that this is the odds of, represents holding everything else constant at 0, the odds of falling versus not falling per unit increase in, for a 1 unit change in trail difficulty. Now, again, the assumption is that sort of increasing the odds of falling is going to be constant, just given the way we've set up our model. But we can change this model to start getting more interesting types of effects there. Yeah.
So to explain that, whenever it's held constant at 0, you can technically write during the spring.
Yeah, yeah. I mean, and that's how you would interpret the intercept, right, for this model, right? What are the odds of falling for people if we? Okay, so how would if we code trail difficulty 0, 1, 2, and we have our 2 indicators for season? What do we how do we interpret the intercept?
It's your constant. It's your
Right. And so, but what's the literal interpretation of that constant?
That's just your likelihood of falling?
The odds of falling if what?
If it's not the other 2 seasons.
Which would be?
What is it, autumn and spring? No, autumn and
Winter.
winter.
Okay. So the odds of falling in spring for, what's our other predictor?
Trail difficulty.
And if trail difficulties if 0 is easy, right? Our intercept is going to be the odds of falling for an individual skiing on an easy trail in the spring. See what I mean? Okay, and so this is where, and this isn't just like sort of fun Sudoku word games to do. Like this starts to become really important when you get into hierarchical linear modeling types of things. You need to know what that 0 point is, and if you start doing that, you can start shifting things around, right? Because I want to estimate this for at this point. Well, then I just make sort of all my my predictor 0 at whatever point I'm interested in, then just measure things and then sort of get my estimator for there, right? So as you're going through, always, and I sort of said this before, you got like literally what does it mean when all my variables are held constant at 0? In this case, it means people skiing on an easy trail in the spring. My intercept indicates the odds based on our model. This is the odds of falling versus not falling on an easy trail in the spring. Okay. Does that help get people squared away with this? Okay. Think about some effect size. We got a couple different things that we can go through and do in our logistic models. You'll see pseudo R-squared statistics. These aren't true R-squared statistics. You can't interpret these as a proportion of variability in your outcome that's attributable to the model. They're kind of generally general indices of sort of your overall quality of your model. Interpretive standpoints sort of jump around for these. A lot of times you see people argue that you don't put a whole lot of faith into these models, but they are something that will come up that you'll see. If you see someone, you read a paper where someone's reported this is a proportion of variability accounted for, tell them no, it's not. For individual predictors, you can, odds ratios in and of themselves are a direct index of effect size, right? Odds ratios is a meaningful interpretation, right? Particularly if we're talking about if we have categorical predictors, right? If you say the odds of developing heart disease versus not developing heart disease increase are 5 times greater for smokers as compared to non-smokers, right? Like that's a meaningful sort of metric, right? So odds ratios in and of themselves can be meaningful, although you want to watch out because you can get odds ratios that are wildly statistically significant, right? So very, very small p-values, but odds ratios that are very, very small. Remember to take a look at the scaling of your predictor, right? Because if you've got a continuous predictor with a wide range, a 1 unit increase may not be much at all, but cumulatively, right, if you're taking those to powers, that's going to jump up really fast, right? We can also, Dell talk about this, converting our odds ratios into Ds. And this might be nice, right, if you just want to have some sort of common metric that people know and understand, right? You want to say this is a sort of large, small, medium, large effect size, taking the natural log of your odds ratio and dividing that by 1.18 will approximate a D based on stuff from Tabachik and Fidel. We can then take D, turn that into an eta squared if you like an eta squared, take your square root of your D over D plus 4. Go back and forth. And again, this is something you want to pay attention to as you move forward with your own stuff, particularly if you're going to incorporate effect sizes, sort of wanting to see general sort of translations back and forth. Generally, these are approximations, right? If you have the information to calculate an eta squared or a D, just do that instead of trying to translate the test statistic. But oftentimes, you won't have that in an article, and but this will give you a mechanism to go through and just try and get a general sense for the magnitude of effects. Assumptions of our logistic regression. Remember that one of the main benefits of these models is they're much less restrictive in terms of your assumptions. Your data can look really ugly. You can have weird stuff going on. And so much more forgiving in terms of having wacky stuff going on in your data that's not going to degrade the inference that you can draw from your analyses. But some things that we do need to go through and take a look at as we're looking at these models. Adequate specification, okay? Models are sort of whatever your model is, variables that need to be in there are in there, those that don't need to be in there aren't in there, right? And again, we don't think about this a lot. We end up saying like, oh, these are the things that I want to have in there. But you need to sort of adequately specify your model and sort of think ahead of time, sort of try and get as much as you can in there to try and make sure that you're not have something that's just crazy bonkers that isn't actually representing whatever your phenomenon of interest may be. Now, we don't have any assumptions about the distribution of your variables, right? So your continuous variables can be crazy skewed. Your can have weird distributions and things along those lines. It doesn't matter technically, but note that you will have a more powerful model under conditions of multivariate normality, right? So it's not an assumption. It just optimizes your model and makes it that much more efficient, right? So these are nice models to go to if you've got like an outcome variable that's just crazy skewed, right? So 80% of your people didn't do anything that you were doing, and then some of them did, right? And so thinking about Katie had her proposal defense today and did a phenomenal job. But one of her outcomes that she's looking at is NSI, right? Sort of self-harm over the course of a 2-week period. That's probably going to be small base rate type of behavior, right? So if she wanted to model this as a count variable, which you wouldn't do with a normal multiple regression anyway, because you're looking at a count variable, not a continuous variable. But you probably end up with a really ugly distribution, right? Mm-hmm. So what you can do is then say, well, we're just going to dichotomize this. We're going to have people who did it, and then the people who didn't, and then just call it that. And for that, that's probably not an unreasonable way to look at those two groups of individuals running this with a regression. But then say, you have maybe like a shame scale that also is really skewed, right? Because most people in my control group didn't have shame, and even the people who do self-harm aren't reporting a lot of shame. But then I got a subgroup of my people who are harming do have a lot of shame, right? So I've got a weird skewed distribution. Doesn't matter for your logistic model. It's fine. You don't have to worry about that. Now, if you have a nice distribution, it makes things just work better. You have a little bit more powerful analyses, but it's not necessary, okay? Other thing you need to be careful of, making sure your outcome isn't perfectly determined by a variable or any set of variables, okay? This can get tricky, particularly if you have small samples, right? I've got 2 categorical variables and a continuous predictor and an outcome, and I've got 15 people in my sample. It may just happen that everybody in my criterion group also happens to be in sort of this predictor versus another, or some combination of those 2 things, and what you end up is a singularity within your estimation where sort of I've perfectly predicted my outcome based on just happenstance between these other 2 things. Everything will fall apart, right? This is kind of the this is the logistic version of multi-collinearity here. Generally, it's not an issue, but it can get that way if you're working with very small samples. You'll see this indicated by a failure to converge large parameter estimates with large standard errors, right? You'll get a, let's say, a odds ratio of 500. It's not statistically reliable, right? Because your standard error is through the roof. Suggests that there's something weird going on there, okay? Need to have sufficient representation in all of our cells, okay? What we're gonna do here is we're gonna go through, run a 2x2, not necessarily a 2x2, but run through our tables comparing our outcome variables, our categorical predictors by our outcome. What we want to have is expected frequencies greater than 1 and with less than 20% of our cells having expected frequencies less than 5. If you've done chi-square stuff and are familiar with that, sort of basically you need to have adequate coverage in your cells so that you're not sort of not having anybody who's actually representing sort of those different dimensions. And again, if you've got a lot of categorical variables, a lot of outcomes, in sort of 8-dimensional space, you can start having pretty sparsely populated cells. Want to make sure you're not having problems there. We're expecting a linear relation between your continuous predictors and the logit. Okay, so remember our logit is the natural log of the odds ratio of our target versus our not target. We're expecting that logit has a linear relation with my continuous variables, right? What we can do to test this is what we'll do is we'll take in our preliminary model, we'll take our continuous predictors and take the natural log of our continuous predictors, create an interaction of those 2 variables, and make sure that the interaction of our continuous predictors and the natural log of our continuous predictors aren't statistically reliable, which would suggest nonlinearity in our logit. Don't want to have outliers or huge multicollinearity, right? We don't want our continuous predictors and our categorical predictors to be correlated one with one another. We don't want to have weird outlying values. Remember, this counts for both our continuous predictors, right? We don't have a lot of assumptions, but if you got a wacky dude way out in the edge of the tail, that can still throw things way off, right? We can also have categorical outliers, right? Sort of this 9-to-1 split in our categorical stuff, but unless you've got a really large sample, you're probably going to catch that because you're not going to have anybody populating some of those cells, right? But again, one, keep an eye on that. And then independence of responses, right? Trent's data should not be related to Candace's data, should not be related to Stephanie's data. We want everything to be sort of independent of one another. But in terms of assumptions about distributions and a lot of these other things, much more lenient, much more flexible with these logistic models, and we should probably be using them more. Okay. Questions on any of these assumptions? Yes?
Linear relation, we take our continuous, we take the logit of them, we make an interaction.
No. So your logit is the log odds of your outcome, okay? And so what you will end up doing is we'll take our continuous predictor and then create a new variable that's the natural log of our continuous predictor. And then what we'll do actually, our logistic analysis will just create that interaction term for us. And so what we'll do is we'll take our continuous predictor, natural log of our continuous predictor, and then just plug that into a preliminary model where we have our continuous predictor predicting in our logistic model, the natural log in our logistic model, the interaction of those two in the logistic model, and making sure that interaction term doesn't come up as statistically reliable. Other questions? All right, cool. Where are we at in terms of? All right. This would usually be our halfway point. People need to take a break or use the restroom or anything like that? Catch a breather, grab another piece of pizza or anything?
I use the bathroom.
Okay, go for it. Cool. All right, let's open up this data set here and grab your handout binary logistic regression. So what we're going to run through an example here, some data that Narina donated. So even when we get out of clinical area, we still have to deal with death and horror. So we like to keep that general thing going in terms of the sets that we're using. Right? And so what we've got here are people who were defendants who were convicted either to life in prison or death. We see this in our sentence variable. The number of VIS, what we're looking at is sort of this depravity score, which I'm not sure what the operationalization of depravity is, but they've done it and put it on a 0-100 scale, indicating sort of the depravity of this crime, and then also looking at the impact of victim impact statements introduced by the prosecution, right? So these are the survivors of victim friends and family talking about sort of what the impact is on this has been to them and how their lives have changed and things along those lines. And also within here, looking at how this victim impact statement was delivered. 0 being none, there was no victim impact statement. 1 is private. What is this, Stephanie, do you know what private refers to? Is that just with the judge or?
Honestly, I don't know. I was nodding my head because I think they're terrible. But,
Okay.
oh, I think they wrote it in private and then read it. Q&A was a question and answer format where the attorney went back and forth. And open was an open dialogue where they just said it on the stand.
Okay. And so some different ways of providing an impact statement to talk about the impact that whatever this person was charged with had on the friends, family members. And so wanted to say whether or not these variables, the number of victim impact statements, how many people are coming to bear for you, the depravity of the crime, and then how those victim impact statements were delivered, impact whether or not people were sentenced to life in prison or death penalty. Okay, and so what we're looking at is a dichotomous outcome with 3 predictors here. Two continuous, or one's variables that we'll treat as continuous, and then 1 that's a categorical variable. Okay? So what we're going to do first, we're going to start sorting these, make sure we don't have any missing data. Okay, so those are all looking good. And so what we're going to do now is go analyze descriptives, and just take a look at number of impact statements, depravity score, and we'll ask, and so we will still need to do this, even though these aren't sort of your distribution of your variables aren't a predictor per se, or an assumption per se. You still want to go through and know kind of what your data are looking like, okay? So we'll go through, take a look at that. And so it looks like we've got anywhere from 0 to 14 impact statements, right, that are going on, and then depravity scores ranging from 2 to 73. The kurtosis of our victim impact statements is pretty fantastically high, right? Both of these are skewed. If we go through and we want to take a look at our, go to explore, and we look at number and depravity score, and want to, there's a histogram. Yikes, right? We've got kind of a,
And there's an outlier.
an outlier there that we probably want to address. That
No,
we-
the data's perfect.
That we will probably want to address, right? And then, same thing, depravity score looks pretty nuts. So we're kind of in a situation here. I don't think that okay. So for this exercise, I didn't do anything with these data, but reasonably, this case here, someone got in over twice the number of impact statements as the next highest. That's an odd thing. We don't have distributional assumptions, and so it's fine if our data are skewed and kurtotic, but that's probably an outlier, right? And so we would probably want to maybe do something to address that. Think about excluding that case probably. I mean, you could smooth it in, but there's just something that, we've got 123 cases. We can lose one case. I'm not, this isn't my field, but it seems something that's maybe odd for someone to have 14. Other thing I would want to do is go through and make sure this wasn't an error in the data entry, that it wasn't supposed to be 4 and someone actually keyed in 14. Go back through, take a look at your data, make sure that this is a case and if it, a valid entry, and if it is, maybe think about excluding that because it looks like it's not generally representative of what else is going on, right? Going down and taking a look at our depravity scores. This is also, we have some it's pretty extreme values, right? Now this would be if you were, this was your data and wanting to think about like what is the best way to deal with this? Do I drop this case? I don't know. What would be nice is if this depravity score is also the person that had 14 people in there, then we fixed that already, right? But again, this is going to constitute probably outliers that you want to probably think about doing something. If it was just these ones, I can probably live with those. That's a little much, right? So wanting to go through, if you're actually doing your screening, wanting to note these, go through, take a look, and then talk about if it was your data set, what you would want to do with these data. Okay? So what we'll do though is we'll leave it alone for the purposes of this, right?
It's not either.
What's that?
It's not the 14.
Well,
No, he only has one.
Yeah, he must have done something real bad. Or she, they.
The delivery was open.
Maybe.
The 14 statements? Yeah, they only had an 11 on the depravity.
I know.
people being dramatic.
It wasn't very depraved, but there were just a lot of people
We just all
around.
wanted to talk about it.
Maybe it was like a public
Uh-huh.
thing, where there were a lot of, well, I guess.
All right, so I'm going to go through and paste these in. Compute. All this. Sync. That. pretend, and we shouldn't, but we'll pretend that our data are fine and we can move forward, right? Which is often your task with our data sets, just so everybody's on the same board, right? But we'll go through and calculate our centered scores, and then go up and just double check, make sure that we've reasonably centered these. Right. Statistics are 0 here, so we're pretty excited about that. We've done this correctly. Okay. So we've gone through taking a look in terms of our assumptions. We would probably note that our data are not likely univariate or are not multivariate normal, given that we've got some weird distributions. We've identified some pretty clear outliers that we'll probably want to take note of, right? And recommend that someone do something with that. But we're going to go through and just deal with it and go through and center what we do have. What we want to do now, I'm going to go to descriptives, I'm going to go to crosstabs, and I'm going to look at my sentence variable, my VIS delivery. I'm going to go to statistics, cells. I want expected, put expected values there, hit continue, paste that in. All right, I'm going to run crosstabs of my continuous or my categorical predictor VIS.
Can you zoom in, Josh? No, I just want to make sure, my eyes are terrible. I just want to make sure I'm doing it right.
Well, you've got your, you
Yeah,
can take a look
yeah.
at your thing there. But yeah, I don't know if we can
It's fine, it's fine.
get these in. But, so what we've got here then is our cross tabulation of our, across our VIS delivery, right? And so Trent, what are we looking for here? What are we trying to screen for?
Just a second.
Why is this cross tabulation important? The number of people in each cell, and what do we want to avoid?
Cells less than 5?
Yeah, we want to make sure that we've got adequate coverage in my cells, right? I don't want to be having some cell in this matrix trying to predict something where there's not adequate representation here. And so again, what we want is we want no expected value less than 1, right? And so if we go through and take a look at our expected counts, those are all looking good. Nothing less than 1. We've got a reasonably large sample, and it looks like this has been sampled pretty well in terms of these different modalities of delivering the VIS. Also, don't want less than 20. We want less than 20% of the cells with expected values less than 5. Expected values less than, or excuse me, we want a small proportion of our cells having expected values less than 5, right? You can have some, you just don't want more than a fifth of those values being less than 5. And if we go through and take a look here, they're actually all above 5, right? So we're doing pretty good here. What are you looking for?
I thought I can't find that one. I was wrong. I have 2 of the same one.
Oh. There you go.
Thank you.
No problem.
See why I'm so confused, sorry.
Yeah, no worries. Okay. So we've gone through taking a look at our distributions. Again, we don't have any distribution assumptions, but it's just nice if our models work out a little more efficiently if we do have nice clean data, but if we don't, that's fine. That's why we go through and we use these logistic models as one of the benefits. We do want to make sure we don't have crazy outliers that are going to screw around things, right? So we want to do something with that. We want to go through and check our cross tabulation to make sure we've got reasonable representation across our categorical variables, and it looks like we're doing okay with that respect. And then what we're going to do now is we want to go through and test the linearity of our logit. And so what we're going to do we're going to compute the natural log of impact. What we're going to do here is we're going to go ln times 1 plus y1 plus number of VIS.
Can't have, zero or negative.
Exactly. So we have 0. We have some people who don't have a number. They have no VIS statements, right? And so we need to make sure that we take care of that. We also want to go through and do the same thing for our depravity score. And again, depravity 1 plus our depravity score. Okay. We're going to go through, calculate the natural log of our continuous predictors. Okay. And so now what we're going to do, so we're going to go to analyze. And we're going to go down to regression. We're going to select binary logistic. Our outcome is going to be our sentence, right? And here what we're going to do is we're going to have our centered impact, our centered depravity, natural log of our depravity and our impact, right? Now what we're going to do, and this is where your logistic models will do you some favors, because what we can do is we can go impact, there we go. So if you go through and you click on impact, centered impact, and then you hit control, and you click on the natural log of impact, okay? So you've highlighted those two. And then you've got this A times B, and that will just drop that in there, right? Same thing with depravity, control, hold down control, natural log of depravity, throw that interaction in there, okay? And then we've got VIS delivery that will drop in there, okay? So what we've got is we've got a model that has our two continuous predictors. It's got the natural log of our two continuous predictors, and it's got the interaction of the actual predictor and then the natural log, and then it's got our categorical variable in there too. And what we're looking at, what are we looking for, Stephanie? What are we hoping doesn't happen?
I don't know. I'm not quite sure.
Anybody? What are we hoping doesn't happen here?
The interactions are significant. We're hoping they're not significant.
Right. We're hoping that we don't have evidence of that we don't have a violation of the linearity of our logit, right? So we go through and we run this, and we're going to get a lot of stuff, but really what we're going to want to go down through and take a look at is our variables in the equation, our very last table here. And got a couple extra things in there. It looks like I actually lied to you and didn't actually put VIS.
Yeah.
No, it's the linear, it's the law, natural laws.
It's just a regular VIS.
Oh, right. Okay.
Don't we need to define
There we go.
the reference group for VIS? Or no?
Yep, scratch that. Let's go back to, so we've got our, taking our natural logs out of there. Okay, so we've got centered impact, centered depravity, the natural log of impact and the natural log of impact and impact, and the natural log of depravity, and then VIS delivery. Which we should actually, just so that we have a proper model here. Go to regression, binary logistic, and probably what we ought to do is go to, click on this categorical up here, and tell it that VIS delivery is a categorical variable. And it doesn't matter which indicator or how we're going to do that. And then go through and paste. So what we've done here is we've told SPSS that our VIS delivery is a categorical variable. It's not a continuous variable. Before it would just, if it went through just 0 to 4, it would treat it as a continuous variable, which actually isn't a thing. Just to do this properly, making sure that it knows that VIS is a categorical variable, and then take it from there.
And it doesn't matter which one we have as our reference group?
No, right?
And why not?
Because we're not interested in that as predictors, we're just interested in whether or not these interactions are significant. So
Okay.
we will get there when we actually run our model.
Okay, gotcha.
Yeah, so this is,
Gotcha.
this
Okay.
is just our screening, right?
Okay.
And so we go through, does someone have a pen I can borrow? Never mind, I got one here. Make a note on this thing, so. So you can see in your handout, we've got an issue where what I've done, at least when I put together this thing, is I didn't indicate VIS delivery as a categorical variable. It's treating that as continuous, which doesn't make any sense, right?
Yeah.
So that should be indicated as a categorical variable, which is why I went back up through and changed that. I'll make a note to change this outcome. But what we're interested in here is whether or not we have evidence of significant interaction effects, right? So again, if we go through and we take a look at our interaction of impact by a natural log of impact, that's clearly not significant. Natural log of depravity and our depravity scores, that's not statistically reliable. So everything else we're not too concerned about. This is just wanting to make sure that we don't have nonlinearity in our logit, right? Because our logit is a continuous outcome. What we want is all of our continuous predictors to have a linear relation with our natural log or our log odds. Here it looks like we don't have any problems with that. Okay? Yeah.
Do we want our natural log of impact and natural log of depravity in there? Not as interaction?
It didn't, yeah, it didn't delete it from when you deleted it.
Oh,
It ran it with everything again.
it ran it with everything again. We'll get it right one of these times. Okay.
It is.
Probably. No, that's perfect.
You're all night now.
I was looking for myself.
Yeah, no. Just use.
You don't wanna review it
like
point it out.
honestly, like as being up here, I get incredibly excited when you guys sort of note the bonehead stuff because it means you're paying attention, you're thinking about it. Not
I just accept it as fact. I'm just like, oh, that doesn't seem, okay, whatever.
No, don't do that. Don't do that, because I sort of screw this stuff up all the time, right? Okay, so if we're going through still not finding evidence of a statistical effect of your interaction terms, so we can say that as you're going through in our screening saying, we do have evidence of linearity in our load shift, right? So have gone through and taken a look at most of the stuff that we really probably need to be worried about. But again, when you're going through and doing your own screening, make sure that you're systematically going through testing sort of your basic assumptions of logistic regression, and even making note of those distributional assumptions and things like that that we wouldn't normally worry too much about, right? Again, Tabachik and they'll do a nice job of working through some of those things. Again, this will be a nice chapter for you to go through and take a look at as well. So let's go through, and so we're, at least for this demonstration, we're going to say our assumptions are good enough or not, because we probably should have done something with those extreme values, right? But we're going to pretend we didn't see those. And we're going to go to our logistic model. Okay, now this time we're going to run this for real and true. And so what we want is we've got sentence as our outcome, right? And then we want our centered impact, centered depravity score, and then we want our VIS delivery, right? So we've got our three predictor variables. Now, again, what's nice about these models is we don't need to go through and physically create indicator variables like we would in a normal regression. What we can do is we can just go through and we can tell SPSS that, okay, this is a categorical variable. Right? Do we need to tell dichotomous predictors are categorical? No. I mean, you can if you want to, but it's not necessary. It's just gonna, we can model categorical predictors as if they were linear, just like anything else, right? But if you've got a multi-dichotomous predictor with 3 or more levels, what you want to do is click on this categorical variable thing, tell it that VIS delivery is a categorical variable, and then what you can do is you can play around with how you want it to model this, right? Base is an indicator variable, right? So you can go through and what it'll do, it'll go through and it'll choose and provide you a coefficient for sort of all your target criteria versus a reference, just like a normal indicator variable would. But you don't have to do that. If you go down through, you can see these contrasts. There's all sorts of different types of contrasts that you can use, right? And these different contrasts do different things, okay? So like indicator, codes present or absence of category to membership. Simple compares each effective category to the last, right? So here it would be 0 versus 1, 1 versus 2, 2 versus 3, 3 versus 4, which could be something that's useful if that's relevant to your design. Difference compares the effect of each category to the average effect of all the other categories. Helbert compares the effect of each category except the last, the average of the subsequent categories. So there's just different types of things that you can set up based on sort of your specific questions, right, that you want to put in the model. But indicator variable is going to be your sort of the basic run-of-the-mill. And we'll probably do most of the things that you'll want to get to do unless you want to start comparing. So category 3 versus category 4, right? That's not going to work within this, right? You've got, so this is my baseline. We're comparing all the others to the baseline. We don't really care about comparing things to each other relative to the baseline. But you can go through and start to get more elaborate with these in the model if you'd like, okay? Other thing to remember is down here, reference categories, reference category the last or the first. In this case, I don't know why it usually selects the last category as the reference category always, but in ours, coding, 0 being none, I want that to be my reference category, right? So I want to go through and collect that first, and I don't know if I would have reverse coded this where no VIS would be my last, then it would sort of change, right? So this is where it's important to know what your variables are coded, how they're coded, and where things go, okay? So we've got told that VIS delivery is a categorical variable. We're comfortable with it running indicator coefficients here. We want the first to be our reference group, and then it's important you go through and you hit change, right? When you hit change, you'll see this changes up here. It says, okay, indicator, parentheses first. Make sure you do that, because if you don't do that, it won't do it, and then hopefully you'll catch it on the back side, okay? You go through, hit continue, and then you go through and look at your options. You can save predicted values, you can save probability, group membership, right here, if you're interested in doing that. You got various residuals and influence measures. These are like multivariate outlier types of things that you can go through and test if you wanted to do that, right? We won't worry about it now, but those are things you can do. Options, we want we'll ask for confidence intervals for our coefficients, right? This is a nice thing we want to do. And again, this is nice because our odds ratios, this is going to give us 95% confidence of intervals around our odds ratios, which should excite the hell out of you, because that means you don't have to do it by hand or create a calculator or some other such nonsense, right? It'll just do it for you. So go ahead and click that. And then there's some different stuff that you can go through and play around with. You're not worried about this right now. So just make sure to click your confidence intervals, and then hit continue, and then stop, and won't worry about that, okay? And then go through and paste. So, here's our logistic model. Go through, I'm actually gonna shut all this down. Yeah. Okay. You got a fresh start here. All right. So first thing we want to do, and always do this, because it's going to help you not make mistakes. Make sure that you've done what you want to do in terms of these models. The number of people that you have in your analyses, right? No missing cases. This is good. We didn't exclude anybody, so things are looking good here. Dependent variable encoding, okay? Judah, what is this telling us here?
Life is 0 and death is 1.
Right? Which one is our reference group?
0. Life.
0, life, right? And so this is good. You want to make sure you don't switch this around, or you've got the wrong coding or something like that, and you're like, oh, depravity, sort of the more depraved your crime is, the less likely you'll get executed, because I sort of switch this around and I'm interpreting this backwards, right? Making sure that you know sort of which variable is which, right? Same thing here, so you got categorical variables, and it's going to tell you how these are coded. Here, VIS delivery, zeros across the board, right? For indicator variables 1, 2, and 3. What's my indicator variable for 1 testing, Trent? My first one. What's my first indicator variable giving me?
That's just telling you that since the people that did not have any VISs, that because there weren't any, that they weren't private, Q&A, or open.
Right. So we've got...
Oh, the number 1 is telling you which that's private?
Yeah, exactly, right? So our first indicator variable, and when we get to our coefficients table, we're going to have an omnibus test for VIS delivery, and then it's going to go down through and it's going to give us specific contrasts. This is saying our first specific contrast in there, and SPSS is going to label this as 1. This refers to private versus none. Number 2 is Q&A versus none. 3 is open versus none, right? And so this is important that you know that this makes sense to you, that this is how you want it to be coded, because if we would have gone through and not changed that default, which one of these would have been our reference group? Open would have been the reference group, right? And had you not going through and taking a look at each part of your output, you might have missed that and started interpreting things as your none as your reference group when that's actually not what it's saying. You've got a completely different thing going on, right? So with these models, always, always, always know and make sure you're 100% solid on what your reference group is here, okay? And then we've got our beginning block. This is telling us for having no variables in the model. No variables in the model, not having any predictors in here, how do we go through and make a prediction on whether or not people are receiving death penalty or life in prison, right? And so Candace, what's going on here? What's this model doing in the absence of predictors? What is it doing?
Which model?
This model that we've done. So in the absence of predictors, if we don't have any predictors, what's the model predicting in terms of whether or not people are getting life in prison or getting the death sentence?
It's predicting whether they're getting life or death sentence based on
no predictors. And who's it saying gets who's it predicting gets life or death, and who's it predicting getting life?
It's saying everyone gets the death.
Yeah, it's saying everyone gets the death penalty, right? So basically, this model, in the absence of predictors, is just saying
Everyone's dead.
everyone's dead. Everyone's dead, off with their heads, right?
Kill them all and let God sort it out.
Why is it doing this?
Because our reference group was life and it was 0.
Okay, not quite. So, not because it doesn't have anything to do with the reference group. Why does this model, in the absence of predictors, just predict that everybody's going to get the death penalty?
because everyone dies.
It's an existential program. It's going to happen eventually.
Is it because you just don't
That's
have
the
anything
constant?
to predict with? Like
So it's,
Yeah.
the lack of having something to use to predict an outcome just makes it go.
Oh, I didn't know. Well, no, it's more systematic than that.
Oh.
Why did what? Go ahead, say it. You're probably right.
No?
Yeah.
Say it.
What were you going to say?
I don't know.
Just
Say something. You were going to say it. And it's right. What are you thinking?
I don't know. It's got something to do with the constant. I was thinking of something.
Yeah, it does have something to do with the constant.
But that's as far as I got.
it's holding life as the constant, and therefore it's saying that it's.
Why didn't it predict that everybody would get a life sentence instead of a death sentence?
Because life is coded to 0?
No. Could a model without predictors have predicted everybody gets a life sentence instead of death sentence?
No?
Could. Not for these data. What's a more common outcome in these data?
Death.
Death, right? So in the absence of any predictors, my best strategy is just to predict the most common outcome, right? And so as long as it's like, in the absence of any other information, I'm just going to go ahead and predict everybody gets the death penalty.
It's just like predicting the mean.
Yeah, exactly, right? And so in the absence of any predictors, models is just going to say, well, we've got 52 people who got life sentences, 71 who got death sentences, but I'm going to go ahead and just predict everybody gets death, and I'm actually right close to 60% of the time just based on these data,
Because
right?
the data has more death than life. Okay.
Right? But
So if the data had more life than death, then it would predict everyone to be in the life sentence?
yep,
Okay.
absolutely, right? And so all this is doing in the absence of any other information, your best guess is just to predict whatever the modal outcome is, and then just go with that, right? And so, and again, reasonable guess given no other information.
Yeah.
And that's good, I hadn't thought about that, but it is just like predicting the mean, right? Like, I don't know, sort of whatever the mean is, that's what we'll guess. We're gonna be wrong a lot, but we're gonna be less wrong than if I would have guessed any other value.
Right.
So that's what we've got there, and I want to take a good look there, because sometimes, so what happens if I'm trying to predict a very, very low base rate event,
That's good.
Not predict this.
right? And so if I go through and I take a look at variables in my equation here, right? What I've got is my coefficient, the standard error of my coefficient, and then my walled, right? if I take the square of that and the square of divided by the square of that, I get my Wald statistic. I get my statistical significance, and then my exponent here, right? But for my just my constant only model, I'm not getting a statistically reliable effect. What does that mean? So I just interpret my constant in and of itself, right? Do I interpret this coefficient here? No, because that's a log odds, right? No one cares about that log odds. It's tough to interpret. But I can go through, and this is where SPSS exponentiates that, right? If we take base e to the 0.311 power, I get 1.365, right?
Mm-hmm.
And this would technically be telling me that the odds of death versus not death, or the odds of life versus not, the odds of getting a death penalty are 1.37 times that of getting a life sentence, right? Or alternatively, I could say the probability of receiving death sentence is about or the likelihood of receiving not a probability. So we're not talking about probabilities, we're talking about odds. So erase probability out of your language in terms of these interpretations, right? The likelihood of receiving death sentence is close to 40% more likely than receiving a life sentence based on this intercept-only model. Okay, but we don't have a statistically significant relationship here. So what does that? And this is not something you would normally interpret, but what does this? What would be our literal interpretation of that constant if we say that's not statistically reliable? What do you think, Trent?
I was hoping the look I was giving you was that I didn't know.
I know, that's fine. Everybody else is avoiding eye contact. You sort of happen to be in my direct line of vision there.
So the odds of getting it.
Is it just that there isn't an odds? It's kind of
Right.
down the middle?
It's not.
Okay, not that there's not an odds,
It's
right?
not different
Well,
from
you can't
zero.
rely that
You can't rely on
that there
it.
will be again. I mean, this
Right.
could just be.
Okay, so yeah, you're close. So it's not that there's not an odds,
It's the same
but it's not
as getting-
zero,
Right.
It's
because
50-50.
It's the
which
same as
is
getting
results in an odds of.
a life sentence?
If it's 50-50, what's my odds ratio if it's 50-50?
1 to 1.
One, right? And so this is just saying that it's not reliably different than even money based on this, right?
So you would interpret it as it's not reliably different from 1?
As it makes sort of there's sort of no difference in the odds of receiving a life sentence versus a death sentence, which makes some sense. I mean, you've got like 50. We've got more people in the sample who've been assigned a death sentence than a life sentence, but not by much, right? And this would say that sort of we don't have enough evidence to say that there's sort of a reliable sort of increase in the odds of death versus life based on just these data in of themselves. Okay. All right. People kind of see what's going on here with this.
Yeah.
Okay. So this variable is not in the equation business. Hold off on that. This is your score test. These are your Lagrange multipliers. This is the intermediate test of your variables. We're probably not going to worry about that. But that's what that is. We'll go back to that and take a look at this in a moment. Okay. Then you get down to So again, just want to make sure people are starting to get comfortable with interpreting their odds ratio. Now, this isn't statistically reliable, right? But we're going to say the log odds of this constant are 0.311. That doesn't mean necessarily anything, but when we exponentiate this out, saying that the odds of death are 1.4 times greater than that of life, right? Or we could say it's about 40% more likely to be sentenced to death versus life in prison, right? But our inferential tests indicate that this isn't different than even money, right? And so we probably wouldn't put too much of an emphasis on this. Okay. Oh yeah, I can do that. That's cool. Okay. So what we're going to do. Variable is not in the equation. Okay, so what what SPSS does is it first estimates a baseline model, right? And your baseline model is your model with no predictors in. And so then what we do is we go through and we test a model with all your predictors, right? And depending on it, you can go through and do stepwise stuff and play around with this if you'd like. But here, we entered all of our predictors in there simultaneously, and we have an omnibus test of our model coefficients. Anybody have an idea about what this test is doing? Or what the equivalent would be in a multiple regression?
I'm assuming the equivalent would be just like omnibus F of the multiple regression.
What's that?
I'm assuming it would just be the omnibus F.
Yeah, absolutely. This is just like your omnibus F, right? This is just a test of your overall model, right? Basically, this is saying, does my model with all my predictors, does it do better than a model with no predictors? Does my model with all my predictors, does it do better than just guessing guessing the modal response? Okay. And so we've got a chi-square test with 5 degrees of freedom, which is statistically significant, right? And so we're going to interpret and say, yes, it looks like our model that has all of our predictors is a better model than a model with no predictors, right? So we're doing better than just guessing the average.
Which
right?
is better, so it's saying, is the model with all the predictors better than the model with no predictors, which is the same as the model with, which is the same as the constant model?
Yep, just a constant
Okay.
model. Yep, absolutely. And so we've got a chi-square value of 21.1. Where are we getting this value? Right, so we're just testing this on a chi-square distribution with 5 degrees of freedom. How did we get this value of 21.05? Look at the table below it and see if that gives you any thoughts or clues.
Oh, it's similar to a Nagel cookie R squared. Well, if you round.
Okay,
move the decimal
that's
place
coincidence.
over.
That's coincidence.
Oh,
Don't worry about
okay.
that. What's the other value in there that we spent a lot of time talking about?
The 2 log likelihood.
Negative 2 log likelihood, right? And what does negative 2 log likelihood tell us? In general, what is it an indicator of?
It's like, kind of like your F squared change.
Okay, good, you're on the right track. Kind of like an F squared change, right?
Broad view of our model.
Okay, model fit, okay. And so again, what we're doing is this is our overall test of our model fit. Do we want lower log likelihoods, smaller log likelihoods, or larger ones?
Smaller.
Smaller, okay. And so if we've got 2 models, if SPSS first estimated a constant-only model, and then it estimated a model with all of our predictors, and we're saying that the model with all of our predictors is better than the model that had no predictors, and our test statistic for this is a chi-square with 5 degrees of freedom, and that's statistically reliable. What did SPSS do to calculate that chi-square statistic?
Subtracted?
Yeah, subtracted what from what?
Two-log likelihood without the predictors?
Absolutely, excellent work, right? What SPSS did in its test of your overall model is it calculated a log likelihood of the model with no predictors, right? And then it went through and it calculated your negative 2 log likelihood for your model with all of your predictors, right? And then so this is a model, this is your log likelihood. It didn't give you the log likelihood of the model with no predictors, right? But then all it did is it took the log likelihood of your model with no predictors, and it subtracted from that the log likelihood of the model with all your predictors in there, and then took the difference of that right? And the difference between that is the number of predictors that you have, right? So we've got depravity, we've got number of EIS statements, right? And then we've got 3 indicator variables, which gives us our 5 predictors, right? So it's testing a model with no predictors versus a model with 5 predictors, hence your 5 degrees of freedom. This is a chi-square difference right there, and a chi-square difference, a chi-square with a test statistic of 21.05 with 5 degrees of freedom, statistically reliable at p equal 0.001. Okay.
Sorry, I was trying to write and listen. So you're saying that the reported -2 log likelihood in the model summary section here
Mm-hmm.
is the log likelihood of a model with no predictors minus the log likelihood of a model with all predictors, and that's what that is.
No, close. What is this?
That's with all
That's
predictors.
with all
That's your log
predictors.
likelihood with all your predictors.
Oh.
What's the difference?
The chi-square.
The chi-square is your difference, right?
Okay.
And it didn't give us that number.
It doesn't give us the other number, but you could figure it out
Right.
on account of addition, right? Right? And you can get that.
That's
right?
faith in me
Right?
that I don't have right now.
So again, so this is your -2 log likelihood difference, right? And this is this idea of nested models, because your model with just your constant only is nested within your larger model where you've got all your predictors, right? And so your model with no predictors is very good. This is a substantial increase in your overall predictability of the model, and so what we would conclude based on sort of this omnibus test of our model coefficients.
So since the model with no predictors is giving us a what is it? Expected of 1, then basically it differs significantly from being a ratio of 1 to 1.
Okay, kind of. You're circling the.
I know the
field.
wording's terrible.
No, and essentially what it's saying, the same thing as it's telling us with our overall omnibus app test and the multiple regression, right? It's saying our best linear combination of impact, depravity, and delivery, natural log of the odds of death versus non-death, right? Basically, it's saying the combination of these predictors provides a statistical improvement in our model, right? So the question being, does the addition of impact, depravity, delivery mode contribute to the prediction? Yeah, it does. It looks like the combination of all these variables together produces a statistically significant reduction in the model log likelihood when we include these predictors in, right? So it's saying we're doing better than just guessing at chance, right? Because if this isn't, basically I've got a bunch of predictors that aren't sort of correlated or sort of predicting anything. They're all useless, right? And so I might as well just predict the modal response, right?
Mm-hmm.
And again, if we go down and we take a look, so here's our -2 log likelihood for our full model, right? And then we've got our pseudo R-squared statistics. We won't care about those too much. But then we've got our classification table. What do we see? What's different about our classification table relative to the last one we took a look at?
The cells are different.
Cells are different. Why is that?
Because we have predictors.
Yeah, we have predictors.
Based off just
And so we're not just predicting that everybody gets the death sentence, right? What we've done, we actually started to populate these cells, right? And based on our model, we're predicting, and again, if you take a look here, the cutoff value, right? So if someone's predicted probability is above 0.5, then they say life. If it's below 0.5, above 0.5, we say death. If it's below 0.5, we say life, right? But what we've done is we've gone from correctly predicting 57% or 58%, we're up to 64. Not a huge jump, but we're certainly better, and sort of our overall model coefficients say that we're doing better than just sort of guessing the modal response, right? So again, if we're going down through and taking a look at this, we've got our true negatives, we've got our true positives, right? We've got our false positives. False positives, false negatives here. And we can go through, we can calculate sensitivity, specificity, all of that within this model, right? So if you actually go through your sensitivities, pretty good. We're pretty good at picking up death sentence criteria, but that's not terribly shocking given that that's sort of the more common response in this set, right? So our sensitivity is 0.76 versus our specificity is 0.48, right? We're catching about half of the life sentences, right, and missing on the other half. Again, positive predictive value is pretty good, 0.67 in this, right? The positive predictive value being our confidence that our criterion is actually a criterion. So if we're predicting someone's going to get the death penalty, we're about like 2/3 sure that that's probably the case. Our negative predictive power is less, but it's still not too bad. It's about 0.6, right? So if I predict that someone's going to be a life sentence, how positive am I? Better than chance, right? Depending on what you're looking for there. And so that's what's going on in our classification table. All right. And then finally, we've got our variables in the equation. This is where we're going through. We're actually looking at our individual coefficients here. Okay. So we've got our constant. What's our constant here, Judah? How would we interpret constant? Okay, so life is our reference, right? So again, remember, what does it mean when all of our other variables is 0, right? So we're talking about average number of impact statements, average depravity, and this actually gets into some collinearity issues because 0 means that there's no impact statement, which conflicts with the fact that average impact statement, right? So here your intercept doesn't actually have a real meaning because it doesn't map onto anything, right? We've got number of impact statements and then delivery of impact with delivery or reference group being 0. And if we have 0, then we can't have an average number of impact statements. So conceptually, it doesn't make a lot of sense given these data. But if we were to say it, we would say for people who didn't give an impact statement at average levels of depravity and average levels of some number of VIS, right? What we would say is that the likelihood of receiving death is 0.8 times that of not death, right? And so for a baseline person, are they more likely to receive death or not death? Or excuse me, whoops, I was looking at the wrong one. There I was reading my coefficient, not my exponentiated, okay? Excuse me. The likelihood of receiving death at average levels of depravity with average levels of VIS for people without a VIS, so ignore that thing. We would be saying that the odds of death are about 2.3 times that of life. Right? So we're about 130 times more likely to receive a death penalty, a death sentence, holding everything else constant at a mean than we would be to receive life. Okay. So again, this makes some sense. All other things held constant, more likely to receive death penalty than not death penalty given these data. Right?
But that's because that's not implying, in this case, it's not implying that most people get the death penalty.
Exactly.
It's just implying that our data shows that because ours.
That's the representative. That's the representativeness that we have, right? And so we're looking at this, and it's not saying anything about the population, right? It's just saying within these data. So if we hold everything else constant at the mean, people are about 130% more likely to have a death sentence than not within these data. Okay? But again, wanting you to go through and making sure people are taking a look at that constant and thinking about what is this, what does it mean, sort of grappling with some of these things. Okay, so we go through and take a look here. So we've got our depravity score. Let's hold off on interpreting that. What's more interesting here, at least from sort of an interpretive standpoint and thinking about uniquenesses of logistic regression, you'll see that we've got our VIS delivery. We have a statistical test here, and then we have VIS delivery 1, 2, and 3. What is that telling us, Candace?
Which one? The statistical test for the VIS
For VIS delivery, and then we've got VIS delivery 1, VIS delivery 2, VIS delivery 3.
Overall, that's saying that overall there's something in VIS delivery that's statistically significant.
Exactly. This is our omnibus test, right? We don't have an odds ratio for this. It's just an omnibus test. Like, does the inclusion of VIS add anything to the model? Yeah, it looks like it does, right? This is a reliable predictor. What about 1, 2, and 3? What is this telling us?
Well, what is it on private, question Q&A and open, or
Versus
predicting
none.
versus
Right.
none?
So
Okay.
these are your contrasts. These are your indicator variables, right? And for your indicator variables, you do have an odds ratio here, right? And so we get a statistically reliable effect for VIS delivery 1, which corresponds to private versus none. Nothing that looks like Q&A versus none, but it does something marginal maybe going on for open versus none, right? So we could make a decision to go through and interpret that. But what we're looking at here is we see, okay, coefficient there, but that's the log likelihood of sort of our outcome. We're not interested in that. But we go down through and we take a look here, and we see our exponentiated coefficient is 0.261, right? And so what we would say is that holding all of the variables, or controlling for all of the variables here, the odds of death are 0.26 times as likely as that of life if VIS is presented in private versus not at all. Okay, and again, my odds ratio is 0.26. So am I talking about an increase in the odds of death or a decrease in the odds of death?
Decrease.
A decrease in the odds of death, right? But I don't have to say, if I'm interpreting this way, I don't have to say increase, decrease, because if I'm saying that the odds of death are 0.26 times as likely as that of life, I'm already indicating in that a reduction in my odds, right? But if I wanted to switch this around, I could take 1 minus 0.261, and I could switch that around. I could say the odds of death decrease by 74% for individuals presenting the VIS in private versus not at all, right? So again, wanting to think about this and sort of put together some language that makes sense to you, that communicates this clearly, because there's some different ways that you can play around in how you want to present this. Right?
So you can use, you don't have to do anything when you're discussing the
Exponentiated.
exponentiated. You can just say 0.261? You
Yep.
don't have, you don't, okay.
It's 0.26, is it, say about 0.25 times the likelihood of not death, right? Which suggests, which indicates that it's a reduction in the odds of death versus not death, right? So apparently, and I said this is probably opposite of what people had intended, but at least these data are saying that if we present a VIS statement in private versus not at all, it actually decreases the likelihood that someone's going to get the death penalty versus not. So I don't know what presenting this in private means, but sort of looks like it actually reduces the likelihood that someone ends up getting a death sentence by about 75%, right?
I think it has to do with the, if you care,
Well.
it's with the emotional content, because they pre-wrote it.
Okay.
So then when they present it in court, it's going to be a little bit less emotional than just on the spot saying how the death affected.
Right.
Sorry.
So if anything, that works backwards against you if you're trying to get people fried up, right? So.
Right.
Fry 'em up. Right.
So do you interpret it as like for every unit increase in private?
Okay.
Ooh,
Now, we could, but does that make do we
Not
need
really.
to? No,
No.
right? Because it's a 1 unit increase means from going from private to, or excuse me, going from not at all to private.
Right.
Is 1 unit, but that doesn't, sort of dumb to talk about it that way, right? Sort of like a 1 unit increase in gender. Like, well, if we, I mean, let's
Right.
just say what it is, right? Sort of relative to males, right? Sort of women are X% more likely to have this happen, or the odds are this percent greater, or this much
Okay.
greater, right? And so in this case, we would say the odds of death are 0.26 times as likely as that of life if VIS was presented in private versus not at all, right?
Okay.
You're just making that
Gotcha.
distinction there, right? Okay, and so then we could go through and want to take a look. So we've got a marginal effect for our third indicator variable. Why might we not want to give up on that guy quite yet?
Because we have an outlier?
Well, that too, right?
Because of the, so this is based off the walled statistic?
The walled statistic, right? And so, you know, this gets a little bit tricky, as in how you test a model without that, because you kind of need that in there. But again, this is one of these situations. If there's a continuous variable, this would be the case where you might want to go through and actually test a difference. And I'm not sure with this indicator variable how you would do that effectively. But if this was a continuous predictor, would want to say, well, let's go through and do a log likelihood difference test to see if this is actually a non-effect or something that we could say, I was going to say, doesn't reach statistical reliability. Okay, all right. Other thing too, if we're going through and taking a look here, we see that we've got an effect of depravity, right? So the more depraved these crimes are rated, it looks like that has an impact on whether or not you're getting life or death, right? And if we go through and we take a look at our coefficient here, our walled statistic, we see that this is statistically reliable, 0.009, so we've got a p-value that would makes us all happy, right? But if we take a look at our exponentiated component, our exponentiated coefficient, looks pretty minimal, right? So we've got a 1.1, our odds ratio is 1.11, right? Suggesting that a 1-point increase in depravity score increases the odds of death by a factor of about 1.1, right? Or we could say that a 1-point increase is associated with an 11%, a 1-point increase in depravity associated with an 11-point increase or 11% increase in the odds of death, which seems pretty minimal, right? But it's really, it's clearly reliable here. Someone tell me what's going on with this.
Well, isn't depravity on a 100-point scale?
Yeah, it's a 100-point scale, right?
So 1 unit is...
1 unit is incrementally small, right?
Yeah.
And so if we go down through, if we want to say, so a 1-point increase associated with an 11%, or a 1-point increase associated with 11% increase in the odds of death, or a 1-point increase associated with an increased, or increase the odds of death by a factor of 1.1. 2-point increase associated with a 23% increase in the odds of death versus not death, right? That's going to be .11 to the second. It'll be something about 0.23, right? If I want to talk about a 5-point increase, right? That's 1.11 to the fifth, corresponding to about a 69% increase in the odds of death versus not death. Right? And if we go back through and we want to take a look at our
standard deviation
for depravity is about 9, right? What is that? Right.
I guess it'd probably be somewhere around 11 or 111%, but
So 1.11 to the 9th is what?
2.56.
So that's
2.5.
So yeah, 256%.
250% increase in the odds of death versus not death for across a 5-point increase in that, right? And so
1 standard deviation increase in depravity would increase the likelihood of the
Oh.
death sentence by 256%.
So it's 9.56?
No, so, okay, whoops. So is 1.11 to the ninth 2.56?
Yeah.
Okay, so corresponding to 156.
Oh, yeah, yeah, 'cause mine's
Percent.
Oh,
Right.
that's
Yeah.
right, that's
Right.
right.
Yeah.
So,
Yeah.
so we would see a 5-point increase would correspond to a 2.56 times the odds of death would increase by 2.56 for a 5-unit increase in my outcome, right? So you're just going through and looking at this in terms of an exponentiating function, or excuse me, as a power function instead of, it's a multiplicative thing, okay? And so we would say the odds of death versus the odds of death sentence, and we can just say, we know what the alternative is, right? The odds of receiving that sentence are 2.56 times that of not death, given a 5-unit increase in this depravity score, a 9-unit increase in this depravity score, right? Alternatively, we could say we see 156% increase in the odds of death versus life in prison, given a 5-unit increase in this depravity score. So just looking at these things as a power function, and sort of these things can start to rack up quite quickly here.
Could you interpret it as just saying a 1 standard deviation?
Yep, you could do that
Okay.
too. Standard deviation
Just
increase.
feeling like that would be more meaningful.
Yeah,
Okay.
yeah, right. And so, excellent. So then wanting to think about how do I communicate this, because this is sort of the big task, right? You run your research and you say, how do I communicate this to people in a way that's meaningful, right? But the one thing to remember, so with our categorical variables, that's easy, right? We say in this group versus that group, right? Corresponds to the odds of this versus that, or X amount times that for this group versus that group. But when we're looking at our continuous variables, because in our model, it's always going to be a 1-unit change unless we go through and start changing around in the scaling of our variable, right? But here, we do standard deviation unit change in depravity is going to correspond to 156% increase in the likelihood of a death penalty conviction. Questions about any of this? Okay. One last thing that we'll do here, just to show you kind of what this looks like.
All right, Josh, I'm sorry, I don't get it.
Round
1.106.
Yep.
Right.
You chose 9 because our standard deviation's almost 9?
Yep.
Okay, but why?
What do you mean?
If depravity increased by 9 units.
That's the standard deviation.
Or more
Right,
standard
we just
deviation.
picked it for fun, really.
Oh,
But if it
okay.
increased by 9 units,
Mhm.
then that's what would happen.
Right,
So
because
one standard
he was,
Which is
yeah,
one standard
Yeah.
deviation
because he
in
was
this
showing
particular
that
case.
although the P is 0.009, that 1.1 doesn't seem very much different from 1, but showing that when
But
you
it-
exponentiate it,
Into something meaningful that would
Right.
actually
So we're
happen.
looking at, because you can say, oh, so given a unit increase, it results in a 10% increase in the odds of death. Well, that seems kind of trivial,
Mhm.
right? But if you consider it that it's a 0 to 100 scale, so that one for just a 1 unit, individually 1 unit increase results in a 10% increase in the likelihood of death. And recognizing that that 10% increase multiplies exponentially across when we start adding things on, right? So that the increase from 1 to 2 isn't, and 2 to 3, we're going to jump from 1 to 3. So if we're just running in 1 unit increases, then that's what it is, right? But it's the same sort of one, it's the same unit increase, right? So you're taking this times this times this times this times this, right? So it's not, if we say a 9-point increase isn't going to be 9.99 increase my odds, it's going to jump it way, way up there, right?
Thank you.
No problem. Other questions about this? All right, cool. Last thing that I want to do, so let's say that we are unhappy with our walled test for depravity. Let's say that we have high moral standards and want to maintain our best statistical tests, and I recognize that if this was statistically reliable with my wall statistic, it's going to be statistically reliable with our best practice intervention here, but doesn't matter, I'm going to go through and do this anyway, right? And so what maybe I want to do then is I'm going to go to Analyze, and first. Okay, so my regression, binary logistic. But what I'm going to do is I'm going to take depravity out of the equation, right? So what I'm going to do is I'm going to estimate a model with just impact, my number of impact statements, and my VIS delivery mode, right? Because what I want to do is I want a specific test, an exact test of the statistical significance of the contribution of depravity in my predictive model here, right?
And why is it depravity?
That
Oh,
is-
because impact wasn't significant.
Yeah, impact wasn't significant, so this is just a demonstration. This is strictly for didactic purposes.
Okay.
This is not because I just picked depravity because it's a category or the continuous indicator that was statistically significant, and so
Right.
it just makes it easier to do that.
So if VIS was continuous and it was significant, you could have chosen that instead.
Yeah, yeah.
Okay.
You
Or
can do
if
this.
it was VIS approaching significance,
Yeah.
that'd be a
Yeah.
good reason.
Or you
Okay.
can do it. I mean, I could leave out
The other two categories?
yeah. I can leave out any predictor I want.
What you're
Okay.
doing is
Oh.
getting an LL difference.
Exactly.
To look at one predictor.
Exactly. What we're doing
Okay.
is going through and sort of manually going through and sort of looking at the log likelihood difference here. So what we're going to do is I'm going to run a model regressing our sentence or the log odds of sentence onto impact and our categorical delivery. Right? And if I go down through and I take a look, my log likelihood for my model with only what happened? I'm not getting the same. Okay. I must have fooled around with this a little bit.
I got what you got.
You did?
On the screen or on the
On
page?
the screen.
Okay,
Oh, yeah, I
yeah.
got what you got on the screen, not on the
Okay.
page.
I need to go through this. It looks like I have an old tables in here. So make a note that the stuff on your handout, you're on the log likelihood there a little bit off. But no matter, we can still run through and take a look at this, because what we're going to do is we can go through and say, all right, so we can go back up and say for our model, that, my full model is right. I don't know what happened with this. Okay, so my model with just my two predictors in here gives me a log likelihood value of 156.713. Right? Minus, and my model with all of my predictors, with VIS in there, right? So this is my model, no depravity, right? This is the log likelihood, the -2 log likelihood for my model without depravity in there, right? But my -2 log likelihood for my model with depravity, 146.519. Okay. Someone tell me what the difference between those two is.
146 is with depravity, right?
146, yeah.
Sorry, gosh, I need to write every step down or I lose it.
Nope, you're good.
10.19.
10.19? Is that what other people got?
10.19.
Okay.
Got 10.134, but it could be my error.
No, totally. 10.194.
194. Okay, cool. So we got 10.194.
There we go.
Okay. So again, I guess people at home, again, what we've done is we've taken the log likelihood for our model that has just VIS and number of VIS delivery and the number of impact statements, which gives us a log likelihood of 156.713, and then we're going to compare that with our full model that has depravity in there, right? And so my log likelihood for that is 146.519, gives me a log likelihood difference of 10.194, and then what do we compare this against, Candace?
A chi-square with 4 degrees of freedom.
There we go. Julie's got it. 1 degree of freedom.
Wait,
Why
what?
1 degree of freedom?
Because in this case, what we're comparing is the with just like the addition of depravities, so it's just
Oh,
that
right,
one.
that just, right, yeah.
Yep. Perfect. Right? And if we wanted to go through and take a look and determine how many degrees of freedom we would have here, go through, look at degrees of freedom here is 4, minus degrees of freedom for our full model is going to be 5. Gives us we've got 1 parameter difference between these two, and so that's going to give us our critical. So our chi-square critical for 1 degree of freedom is 3.841, right? That much larger than 3.841, right? So we've got a clearly statistically reliable effect. If we go through, so chi-square of 10, what is it?
10.194.
194 with 1 degree of freedom. Gives us a p-value of 0.001, right? So you get a, right? And so even for this, right? Even for this, we didn't need to test this because it was already statistically reliable with our walled, right? But still our walled p-value was 0.009. We're even still seeing a reduction here in terms of at 0.004, okay? And so again, this is how we can go through and start comparing nested models to get a specific test of whether or not the addition of this one variable starts to go through and make a reliable difference. Now if we go back up and take a look in our full model, we've got our Lagrange multipliers, right? Our score test here. Remember, this is our intermediate test. It falls somewhere between the walled and our log likelihood difference. We get a depravity p-value of 0.009. So that's actually not a whole lot different than walled. The idea being, if we were to exclude from using a Lagrange multiplier, the score test, so what would be the reduction in our model given the exclusion of depravity, right? Now, if we wanted to go through and do the same thing, get a specific test of our categorical VIS delivery mode, we could do the same thing too, right? We could go through and we could run a model with our 2 continuous predictors, leaving out depravity, compare that against the model with run the two models with our continuous, leave VIS delivery, our categorical VIS delivery out, and then compare that log likelihood of the model there against the log likelihood of the model with VIS delivery mode in to get a difference there. How many degrees of freedom would we be testing that against, though?
Well, there are 3 different categories, right?
Three,
So
right. 3, right? And so if you want to go through, if you want to make sure that you're strong and solid on that, take the degrees of freedom from your full model, subtract from the degrees of freedom of your restricted model, and that's the difference in your degrees of freedom. That's what you're going to test your chi-square against with this. Okay, and so this is something that will continue to come up. If you go through and you start getting into structural equation modeling and things like that, this chi-square difference test is a big part of going through and testing models and sort of determining whether or not sort of we need these within SEM. A lot of it is, do we need all these parameters, or can we start fixing some stuff to 0, and does that appreciably decrease the overall model fit? Here, what we're looking at is sort of, does the addition of this increase our, or sort of substantially decrease our log likelihood? But again, this is going to be our test. So wanting you to know how to go through, know what these values are, what they represent, and how to manipulate them appropriately to get strong tests of individual coefficients, overall models, and things like that. Okay? Questions?
Yes. So you could do this test with sets of predictors if you wanted.
What's that? Oh, yeah.
You could do this with sets of predictors if you wanted.
Absolutely.
I mean, doing it with a categorical variable is essentially doing it with a set of predictors.
Yep.
Right?
Absolutely. Absolutely. And so I could go through and I could say, thinking about using this as the same thing as like a hierarchical model, right? Where I want to say, all right, does the inclusion of this set of predictors contribute to the predictive value of the model? Absolutely, right? Because you always want to make sure you've got a full model that has everything in it, and then the restricted model that's only has a subset of those. What you wouldn't want is in your restricted model to have a variable that's not in your full model, because then
Right.
that's going to be weird, and your degrees of freedom wouldn't correspond the way they should. You would probably catch that if you were, you might end up with, yeah, it wouldn't pan out correctly. So, but you can go through and start to do these. And people who use a lot of categorical data analyses, there's a whole lot more that you can do with this. This is just a very, very basic introduction to logistic models. But we'll have you go through, play around with these a little bit, work on and practice interpreting these coefficients, and then take things from there. Sound good? Questions on the ends? All right, well,
Yeah.
let's call it a wrap. Let's not worry, unless people want to get into sort of repeated measure stuff. Stephanie's tapped.
Do it anyway. So. Yeah.
How about this? The first part of it is all pretty much the same thing, because we just kind of went over it already in the ANCO stuff. Actually, let's not worry about it. We'll catch up with everybody. We will sort of get everybody on the same page. These repeated measures analyses are going to be kind of a bear in terms of sort of we're going to close out sort of with these repeated. They're just kind of complicated analyses to go through, and so we'll get everybody. We'll start with everybody, get everybody on the same page. But the first half of that presentation is going to be pretty straightforward, because it's just reviewing sort of our ANOVA models, partitioning variability into within and between and things like that. We'll sort of sectioning out a repeated measures component of that, and sort of use that to increase the power of our design. So, but we can cover that on Wednesday when I get back. So, sound good? Awesome. Hey, thank you guys so much for coming. I posted data sets and problem set for problem set 6, so you can go home, go through, get started on that. Not tonight, don't start. Or if you want to, do that. If it's fresh in your mind, you're like, nope, this is a good time to do it.
Is there any repeated measures on it?
What's up?
Are there any repeated measures on it, or have we covered
No,
everything?
no,
Okay,
no.
so we've covered everything.
Yeah, this is all straight up logistic stuff.
That's what I was hoping.